Okay, when you look at two lines in general, when you look at two lines in Rn, so you look when you talk about lines in Rn, you always think about vector equation like this or associated Cartesian equation. When you think about these two lines, there are three possibilities for them to interact with each other, and these three possibilities they express like this. One of them is when they intersect in some point, and that possibility, that geometric possibility, algebraically, you test for that possibility like this. You just look at the equation. You just equate the right-hand side of both lines to each other, and I draw your attention to this little fact that I rename the parameter in the second line to distinguish it from the parameter in the first line. These are two different parameters, so you have to use two different letters, lambda and mu. So you equate the right-hand side of both lines to each other, and you try to solve for each parameters if you can find any pair of parameters which will make this happen. And that's how you test for the intersection of the point. Effectively, intersection in one single point equivalent to this system having unique solution. We'll practice this in a sec. Now, the other possibility which might happen, so I call this system star. Actually, I have something more to say about this first possibility. Now, if you look at this equation in this form, if you just rearrange this equation a little bit, if you put it in this form, if you put all A's on one side and put all B's on the other side, it will take the form like this. A take A1 equal to this. And now you can say, you can express this now in our advanced language, in the language of spans, because what you see here in front of you right now, this last identity, in the span language, it just says to us that this difference belongs to the span of the vectors b and b1. So that's how abstractly you can analyze what happens when the two lines, general lines in Rn, they intersect in the point. Algebraically, this just means that this system, which I marked with asterisk, this system has a unique solution. In the span language, it means that the difference of vectors, difference of position vectors A and A1, belongs to the span of B and B1. Good. Second possibility, which might happen is the possibility when lines are parallel. Let's just see what happens in this case. Or actually, let me ask you this. How we can qualify, how we can describe this second possibility, the lines being parallel, in terms of the system which is marked with the asterisk. What should happen to that system? You have to say two things. First, you have to say that there is no solution to this equation. It's the first thing you have to mention, because your lines, when lines parallel, they do not intersect. So if they do not intersect, this system must not have any solution. But this is not enough, because two lines may not intersect but still be not parallel. You have to put another thing on, which is the b vector parallel to the b1 vector. That's the direction vector of your line. If I just zoom out for a second and bring it down, remember the b vector was the one which gives me the direction of the line, this one. So if I have two lines with separate b vectors, b and b1, if these two lines parallel, their directional vectors will also be parallel. So the scalar multiple you should put not next to the L, formally speaking. You were close. It's just you almost spot on. You should have told me that B is a scalar multiple of B1 rather than L scalar multiple of over 1. But apart from that, that was the closest answer to the correct one. So we have no solution to this system, plus we have B parallel to B1. Now, if I ask you, in my advanced language, B being parallel to B1, in the advanced language, how do we say that? We say that these two vectors are linearly dependent. That's how we qualified this being parallel in our advanced language, in our advanced terms. Now, we have these two possibilities, intersecting the point and being parallel. Do we have any other possibilities? Or is that true that these two cover all possibilities? in general, the answer is no. There may be another possibility when you still don't have any solutions to the system, but this is not true. When these two vectors are still linearly independent, so you don't have any parallel thing. And that's the third possibility, which we call skew. If you haven't seen this term before, it's the first time. That's how we call this possibility. Two lines being skew when none of these two happens. They don't intersect and they are not parallel. So no intersection point and non-parallel. And now if I try to classify this case in terms of my system, look what happens. Look what happens if I classify this in terms of my system. How do I do that? Yes, we do it like this. It means that, well, this one, of course, came from the negative of this, correct? This came from negative of this because skew lines, those lines which do not intersect. Intersect is equivalent to this, difference being in span. So if they do not intersect, difference is not in span. First negative statement. Second negative statement is this statement, that this is also not true. So in fact, these vectors, b1 and b2, they are linearly independent this time. So that's how you can classify this third possibility that the lines are skew, is when the difference of position vectors doesn't belong to the span, and when the vectors b and b1 linearly independent. Well, I gave you this little picture. How it normally happens when you have two skew lines is one just like non-parallel to the in three-dimensional space. This may happen. You have two lines. One is hanging above the other. They do not intersect and they are not parallel. And that's the typical skew configuration of two lines. I can take this classification a little bit further. In fact, unfortunately, last time I skipped this one lemma. One result, rather like an abstract result about linear dependence and linear independence. If I have time today, I'll show it today. Otherwise, it's in your yellow book in one of the tutorial questions. You will see this question and one of your tutors will do it for you. The question goes like this. It says that if you have a pair, in fact, I'll give you the statement. It goes like this. If you have, no, it's a different statement. It's here. It's the second part of that lemma. If you have a set which is linearly independent, like for instance for two skew lines, two vectors which produce these two lines, they are linearly independent set of two vectors. If you have such a set, and if you have a third vector or another vector which doesn't belong to such set, or in fact this is a typo, I just realized, which doesn't belong to the span of that set. If you have another vector which doesn't belong to the span of that set, and that's again our case, then you can say that if you extend your set with this new vector x, the new extension will also be linearly independent. So every time you just add up a vector to a set which doesn't belong to a span of that set, you end up with a linear independent new bigger set, but still linearly independent. Okay? I'm sure there is a question like this in the yellow book. I don't remember the number. It's not really a difficult question, but it requires some careful abstract manipulations with these concepts: linear dependence, linear independence, and span. There is a proof here on this slide. If I have time, I'll show you. Otherwise, you'll see it in the tutorial. So let's just go back down to my lines. Look how this lemma will help me now to make interesting conclusion. So we just discovered with you, if I have two lines which are skew, it means that the BB1 vector is linearly independent, and this third vector doesn't belong to the span. According to the lemma, I just showed it to you, this new set, if I take this new set, so if I extend my BB1 set with the new vector A take A1, this new set will also be linearly independent. We just did it with you, okay? Now, think about this. If you think about planes, plane, R2 space, then we saw it with you. The plane, simple plane, it's a span of two vectors, right? It was always, it's a span of two of these standard basis vectors, I and j. And as like last time, we just come to you, well, we will come across this result which says if you take vectors from a span of two vectors, as soon as you took three vectors, no matter how you pick them, no matter how hard you try to pick a good or bad vectors, the three vectors will already be linearly dependent. Remember that? Last time we just discussed, well, it was actually, there was an example. There was an example in your lecture notes which took us to this idea. If you take more vectors from a span of, if you take more vectors from a span of some particular number of vectors, so for instance, from a span of 2, if you take 3 already, this 3 will be linearly dependent no matter what. And so where I'm heading to is this: if you live on your plane only, these 3 vectors, if they come from the plane and the plane of span of 2 vectors, these 3 vectors will always be linearly dependent on the plane because they come from a span of 2, and you already have 3 of them. And that actually explains to us why on the plane you never have skew lines. It explains to us in the abstract algebraic terms why on the plane you will never have this third possibility for the mutual disposition of 2 lines. To have this third possibility, you have to go at least to the dimension 3 to make these 3 vectors linearly independent. Okay. Any questions? It's rather abstract view on this issue, and you might find this excessive because you saw planes very well. You know their nature, their geometry. But still, it's a good way of looking at things with these higher concepts, and this way of looking at things actually has an analogy in the higher dimensions where you don't have your experience with the geometry anymore.